Okay, so the first question, what's the major product for the following question? You see this one? The major product. So, like this, right? And then there's a metal group here. So there's a metal group here. So I just put Me. Or we just fill this place. But here I just want we can use this. So they're the same thing. Okay, they're the same thing. And then this is what? This addition reaction under acidic condition, right? Under acidic condition. And then the first step, you can just imagine, when proton attack here, right? And then we'll get this. So you get what? You get a secondary carbocation, okay? But surely there's another possibility the proton can attack here, but we know if you attack here, we get what? Primary carbocation, which is less stable, right? So this site, is preferred. So this route is preferred for proton to attack here so that it can carry positive charge. Yeah, why? Because if we draw, right, because this proton has no electron, then one electron need to move from here to here to satisfy hydrogen. Therefore, then there's positive, then it will form carbocation. Okay, carbocation here. So, but we know this is what? This is a secondary carbocation, right? Secondary. And then you see there's when you see acidic condition and carbocation, and there is methyl, there's an alkyl group nearby. You see there's what? Hydrogen shift. Hydrogen shift. We briefly mentioned this. So the hydrogen here can shift here and take an electron with it. And then we get this. I'm sorry. Now, this should be planar, right? Because what? This is sp2 hybridized, right? sp2 hybridized. Now this is a tertiary carbocation. Tertiary carbocation is more stable. Is more stable. There's a rearrangement. And we often talk about carbon rearrangement, but here it involves the proton shift, the hydrogen shift. The hydrogen shift. You might ask, why not this metal group shift here? It's also possible. But you see, chemistry or the route of any chemical changes also always choose the least resistant route, right? So it's easier for this proton, for this hydrogen to move here, rather than for this to move here, right? It's also possible, but it's not preferred. You see, we talk about the major product. We always choose the preferred route, the preferred product. And in chemistry, the preferred products always come from the low energy route, the more stable route. So you see that this rule, we use it from the beginning to the end. And then, because this is, you see that sp2 is planar, right? We discussed this in general chemistry, it's planar. So it's planar. And then there's a possibility for this bromine to attack from here, right? To attack from here, then we get, this is above bromine, bromine here. And then if bromine attack from the top, then the methyl group should be here. Or the bromine can attack from behind the screen. So this is enantiomer, okay. Okay, so to save time, I will draw it. The enantiomer is this. And you can see they have opposite chirality. You switch this, right? You switch these two. You switch any two groups of 4 attached to the same chiral carbon, then the chirality change. They are enantiomers. So that's question 1. And then question 2. Question 2 is what's the major product? For the first one, we got methyl group here. You see, for this one is what? This one is water addition. Follows what rule? Mark rule, right? And then you can see here, the proton will attack here. Why? Because if the proton attack here, then the carbocation, the carbocation will be like this. So this is more stable. This is more stable. I'm sorry, this methyl group. Sorry. Yeah, when the proton attack here, you form a tertiary carbocation. Surely proton can attack here, but then it forms secondary is not preferred. So the proton prefer to attack here to form a tertiary carbocation. Right? Tertiary carbon is more stable, it's very stable. And then the chlorine will, okay. So chlorine here. And then the second step for this reaction, the second step is what? Tertiary butoxide. And potassium butoxide is bulky, right? This is bulky. Tertiary potassium butoxide. This is what? This is bulky. This is very big, right? Tertiary, the butyl group. Remember, in hexane, in cyclohexane, the butyl group always sit at a equatorial position, right? Equatorial position, because so as to have the lowest energy. Why? Because this is so big. When this is big, it follows what? It follows what rule? For elimination, there are 2 rules, right? For elimination, there are 2 rules. And when this is bulky, it will follow the Hoffman rule. So when this is not bulky, it forms what? Zaitsev rule, right? The other one is Zaitsev rule. This follows the Hoffman rule. The other one is Zaitsev rule. And then when this rule is applied, which product is preferred? So there are two. Okay, there are 2. You see, either the hydrogen here and the chlorine here are eliminated at the same time to form this. Or the chlorine, because this is what? This is chlorine, and this is called alpha carbon, beta carbon. This is also called beta carbon. This is beta carbon. Okay, but these 2 beta carbon are equivalent, right? These 2 beta carbon equivalent. And then for this elimination, the hydrogen, the beta hydrogen, will be removed. So there are 2 possibilities. This rule, right? There are 2 possibilities. So which one is more stable here? Which one is more stable? This one is more stable. Why? Because this one is more stable. Because double bond, this double bond is electron deficient. Electron deficient. That's the reason when you see the chemical shift for AMR, for the hydrogen attached to double bond have higher chemical shift. Why? Because it has a lower chemical density. Yes?
Is that because it's within the range?
To be more precise, to be more precise, we need to say, because this double bond has how many? 1, 2, 3 substituted groups, and this has only how many? 1, 2. Because you see that this CH2, CH3 can donate electrons. Why? Because this carbon is attached to what? To hydrogen. It can grab electrons from hydrogen. Therefore, this carbon is electron rich. And then it can, then this double bond can kind of share the electrons from here. So, yeah, so this carbon is, CH2 and CH3 are both electron donating. Because this double bond is electron deficient, lacks electrons. It wants more electrons. And then these two groups can have this purpose. But then these only have 2 of them. And this has 1, 2, 3 of them. So there are more groups. There are more electron donating groups connected to this double bond, connected to the 2 carbons in the double bond. So this is more stable. And then Hoffman rule, according to Hoffman rule, this will dominate. And this is what is Zaitsev rule. Or maybe, I think, well, something like that. Zaitsev rule. Yeah, this is Zaitsev rule. This is, you see, this is Hoffman rule. So the answer should be C, right? Because we use this bulky alkoxide. Then it follows this Hoffman rule. So you see, that's also the reason, this is electron deficient. That's the reason for the carbon NMR, the chemical shift for carbon 13 for this double bond also have higher chemical shift because this is electron deficient. So let's see question 3. What is the chief product for this acid catalyzed? So 2,5-hexane, right? 2. This means 2. Hexane means the double bond here, carbon 2, and then 2 methyl group. 2, 3, 4, 5. Okay, this is starting material. And then acid catalyzed. So it's acidic condition in water. So we can just simply put this. And then, again, the hydrogen prefer to attack here, right? Why? Because when the hydrogen attack here, we got a tertiary carbocation. And then the OH group in the solution. Very straightforward. There's no, because it's very stable. And then for question 4 is kind of straightforward. So question 4. Question 4. I mean, this is a what? Oxymercuration, demercuration. Okay, it's very, because it's in water. Okay, in water. So if it is in alcohol, then we get what? Ethers, right? As we discussed yesterday. So then this is a mark addition, right? Mark addition. Mark addition. This is what? This is radio selectivity. But we know for this mercuration, demercuration, there's no stereo selective. Meaning there's no cis trans. We have both, the product of both. So mark addition, you see the proton should go what? The proton should go to the carbon with more hydrogen already. So the answer should be B. Okay, to save time, I will not go because we're quite simple. We follow this mark addition. Then the hydrogen should go to the end, right? Mark addition. Then the hydrogen should go to the carbon with more. The hydrogen should go here. So the hydroxy group should go here. And then there's what? There's no stereo selectivity, meaning we have both. So you got this. I mean, here, you see that this carbon is chiral. There are two possibilities. So it should be a pair of enantiomers. So the answer should be B.
Dr. Yao?
Yes?
Sorry, how did you know that it was stereoselective, or not stereoselective?
Very good question. Yeah, I remember this chapter 8, table 8.1. Table 8.1. There's a summary. Table 8.1, page 358. Table 8.1. So for this oxymercuration, that's okay. So, yeah. So you see, not controlled, meaning you have both. You have both. The good thing is that because it's not in acidic condition, this is not in acidic condition, then there's no rearrangement. The rearrangement can complicate things, and in chemistry, in chemical synthesis, we want sure things. We don't want anything that can. We don't want any complications. So this is assignment 1. We finished assignment 1. These 3 is summarized. I mean, these three methods are summarized in table 8.1, page 358. So, for this, for question 1, again, we assignment 2. So question 1, we first draw the structure. Okay, 3. Okay, so there's one thing. The reaction is very similar to this one, but in terms of, we need to pay attention to the naming. 3,3-dimethyl one cyclopentane. You see that? This is double bond, right? This is double bond. This is double bond. When we count the number, when you count the position number, we can count from here 1, 2, then 3. It's like that. Yeah, we need to follow 1, 2, 3. So we cannot say this is, so this is correct. We start from here, 1, 2. So you cannot do things like this. You cannot say this carbon 1, 2, 3. So this is wrong. Okay. You see that? This 1, 2. No, 1, 2. Then this 3. Then this is 4. What I mean that when we write this structure, we need to pay attention. So you start from here, carbon 1, 2, 3. You cannot draw like this. 1, 2, 3. No, you cannot, because if you we put the double bond here, then the double bond should follow carbon 1. You see that? So this is wrong. I hope I don't confuse you. This is wrong. This is wrong. Yeah, if you draw that, it's 1, 2, 3, 4. You cannot start from here 1 and then 2 here. No, you cannot. Right? So this, yeah. And then you see this is also what? Oxymercuration and then oxymercuration and demercuration. So it's marked addition, and there's no there's no stereochemistry. So you will get a pair of enantiomers. So the answer should be C. Okay, the answer should be C.